Cite that the number of coronavirus cases goes up every day. Here is the graph of the total number of cases from February 26th to March 11th, which rises pretty alarmingly by 50% in these 15 days. Another Channel 3 Blue 1 Brown already said that we should expect a logistic curve for the number of cases, but there are two questions we want to know about this curve. First of all, what is the plateau? Is it the entire world population? Or 27% of the world population, like in the Spanish flu in 1918? Another question is, when will the number of infected cases be reasonably close to this plateau? In other words, when will this epidemic practically end? Is it July? Will the coronavirus persist for a year or even an entire decade? On the hopefully unlikely assumption that things go as is now, the plateau is somewhere around 1.87 billion, and the approximate time frame for the entire epidemic is 4 to 5 years. But you want to know where these numbers come from, and more importantly, whether you should trust these numbers. The epidemiological model I'm using is called the SIR model, which is one of the simplest, although with reasonable accuracy. It compartmentalizes the entire population into three parts, which are labeled as S, I, and R respectively. S here stands for the susceptible population, and the initial value is taken to be the entire world population because this is a novel virus where nobody has immunity. I stands for infected population. These are the people currently ill, and we don't know whether they will recover or die from the disease, which is taken to be around 53,000 as of March 11th. And R is supposed to stand for recovered population, but here I put recovered in quotations because we have to take death from the virus into account for reasons explained shortly. This is taken to be around 73,000 as of March 11th. Just to be clear, the vast majority of these 73,000 is recovered. For an infection, people first go from being susceptible to being infected, then to the quote-unquote recovered stage. The main reason we put death in this R stage is that whether you recovered or died from the virus, you can't infect others and can't be infected, and this model only cares about the spread of the disease. We also have the sum of these populations to be N, the entire world population, and we take this to be roughly constant. The model relates the dynamics of S, I, and R by some simple equations. Here they are. It looks complicated, but it really isn't. These two terms are really the same, just with opposite signs, and these two terms are also different only in signs. When we go back to our basic three-part model, all these equations mean is that the rate of the first transition is proportional to both S and I, and the rate of the second transition is only proportional to I. The reason we think that the rate of first transition is proportional to S is that the more people who are susceptible to the disease, the more people will get infected. And the reason why this is proportional to I is that the more people infected, the more people will get infected. And the rest of this expression is just the constant of proportionality. Now for the second transition, the more people get infected, the more people recover or die from the disease each day. So these equations now make more sense. And we want to find out the constants beta and gamma for coronavirus. To do this, we just need to find some data on daily new cases, whether it is newly infected, recovered, or died from coronavirus, and the data of S, I, and R on the previous day. And you can do this by visiting the Worldometer website. The value of beta and gamma seems to be changing every day, but we can still take the average. And the result I obtained is that beta is roughly 0.0724 and gamma is roughly 0.063. Based on these values, assuming that they don't change over the course of the epidemic, we will get the figure I presented in the beginning of this video, i.e., the total number of cases combining both currently or previously infected will reach a plateau of around 1.87 billion. Now this figure is very horrifying to say the least, because that amounts to a quarter of the entire world population. These so-called constants beta and gamma are super important in the entire model. We took this set of constants and we end up with a plateau of 1.87 billion within a timescale of around 4 to 5 years. This set of data we obtained is the average of the betas and gammas we get over 15 days. However, if we look at the most recent data averaging over much shorter time, we get this set of more horrible constants. The reason why it is more horrible is that the plateau is at 6.6 billion, and the timescale is at around 10 months from now. The difference here is the value of beta increases by a lot, and the value of gamma is much lower. This means that the ratio between beta and gamma increases by a lot, and this ratio pretty much determines the behavior of this epidemic. This constant is so important that we usually call it the basic reproduction number. It roughly corresponds to the expected number of new cases from one single infection. If this ratio is bigger than 1, we are still initially in the exponential growth stage, like right now. And if this ratio is smaller than 1, we will be in exponential decay. In fact, if we set beta to be 0.05 and gamma to be 0.06 so that the ratio is less than 1, the plateau will be at around 390,000. And this epidemic will practically finish after around 20 days. That means around early April. But the problem is how to change these constants so that we get this optimistic scenario. We can approach this in two ways, namely decreasing beta and increasing gamma. Recall this model that we saw previously. Beta appears in the first transition and can be thought of as the likelihood that a susceptible individual becomes infected. And gamma appears in the second transition and can be thought of as the likelihood that an infected individual recovers or dies. So to decrease beta is the same as decreasing the likelihood of infection, and increasing gamma is the same as increasing the rate of recovery. For decreasing beta, it can be done by stricter government border control, which not many are doing well, and whether or not you are infected, staying at home as much as possible decreases the chance of infections happening in the first place. Of course, observing personal hygiene is also important in decreasing infection. Developing vaccines can also decrease the value of beta significantly, but this definitely takes quite a bit of time to do. For increasing gamma, however, there is not much that we can do about, other than developing better medicine to treat patients. These are of course quite common sense, but this video hopefully shows how powerful these measures can be in the long run. If you enjoyed this video, give it a thumbs up and share it. Don't forget to subscribe with notifications on for more of these math videos. See you next time!